This is Physics 2212 at Georgia Tech, Lab 4, The Magnetic Field of a Bar Magnet by Samantha Hefner. So the purpose of this lab is to look at or measure the distance dependence of the magnetic field due to a small bar magnet, and then we're going to compare it to the distance dependence predicted by the equation for the on and off axis magnetic fields derived from the Biot-Savart law. Some of the models and fundamental principles of this lab, the two main ones are the Biot-Savart law and distance dependence. Quick preview, we get a mu value of 2.6 amperes times meter squared and an n value of about 8.76. So here is just a quick visual of our models. On the left here we can see the dipole-like magnetic field of a bar magnet, which is going to do a lot in dictating the distance dependence that we observe. And then we have laid out here our distance dependence formulas, our Biot-Savart formula, and some of the things we're going to use in our calculations later on. So here's a quick visual of the experiment. Some assumptions that we're going to start with is that the x-axis points along the width of the phone, the y-axis points along the length of the phone, and the z-axis points out of the page or the screen. Also, we are going to take our system to be the bar magnet and then our surroundings to be everything else around it. So here we see our bar magnet, we've got a ruler right here, or a meter stick, then we have our phone. So with the procedures, first thing we do is we're going to identify the location of our magnetometer on our phone by kind of sliding it up and down along the ruler. The ruler is oriented east or west, and then we're going to place pieces of tapes. And this little X right here is just kind of where the sensor is and where we're kind of going to be basing all of our measurements off of. So kind of like calibrating it in a way. Okay, the next thing we do is we're going to determine the distance between a sensor and magnet needed to produce several specific magnetic field and magnitude. So you'll see in the next slide with our graph just that we started off with like how much distance does it take to have a magnetic magnitude of 100 or 500 or 50 and then we'll plot those distances. So here you can see R20 is the distance needed to have a magnitude of 20, then a magnitude of 70, 120, 170, 220. It graphs all of this, and then you can kind of see like the downward trend, which is kind of what we want to see, and it kind of goes along with the distance dependence. So some observation is that the x component of the magnetic field increases the closer the magnetometer is to the magnet, and the magnetic field decreases with distance from the magnet. So here's some calculations, just a quick little summary of what we kind of did. Our n value and ln of b is pretty easy. So the graph obviously just kind of, you can produce the formula for the slope. Our n value is actually the slope of the graph, so negative 8.76. ln of b is the y-intercept, it's 23.345, and then using this we can get k, and all we do to get k is just we're isolating this b, e to the 23.345 is our k value. We get 7.268 times 10 to the negative 11, and then we are going to end up plugging this into the Biot-Savart law. Both the k and the n are going to go into that to get us a mu value of 2.6. Alright, here's our code. So we start by kind of like labeling our axes or orienting ourselves. We're going to use this to draw 2 arrows representing the magnetic field on the x-axis, then 4 arrows perpendicular to the x-axis. And then when we plot this all out, it looks like this. Okay, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? The accuracy of our results would be negatively affected because the Earth's magnetic field would skew our measurements. And if we were to stick 2 identical magnets together, end to end, and run the experiment, how would you expect your measurements to differ? We would expect the magnetic field measurements to be larger, but the direction would be the same because it's still kind of laying it out in the same direction. But 2 magnets will just make it stronger. All right, so in conclusion, we observed the distance-dependent nature of the magnetic field, and we got a mu value of 2.68 times n squared. Thank you.